So here, let's identify the connected and disconnected graphs. As a reminder, a graph is connected if you can go from any vertex in the graph to any other vertex in the graph, though it might take a long path to get there. Now for this graph, as we look, do we agree it would be a connected graph? Okay, what about the other one? It's disconnected. Now, what would you say if somebody said this, though? But it seems like this part is all connected. Because it is, but do y'all see kind of the square underneath? There's no way to get from what I've highlighted in pink to the square. So even though two parts of the graph are connected, the third part is not connected. Does that make sense? So the graph is disconnected. And if I could imagine kind of pulling this away, all the top part would come away and you just have the square that's separated. Now we've got two problems here. Problem 1, problem 2. If y'all would think for both of these, whether the pair drawn would be isomorphic or not, remember the first thing is isomorphic is saying it's encoding the same information about the connections, but it might look slightly different because we know that the lengths of the edges don't really matter. You can shrink or you can stretch an edge. Also the location, so imagine the edges are very bendable, so we can kind of constrict them, move them around. And one of the first things I check is there the same number of vertices? Because if not, it's definitely not isomorphic. Is there the same number of edges? If not, it's definitely not isomorphic. And then if there's the same number of edges and vertices, you ask yourself, okay, let's start comparing degrees. Are the same number of degree vertices connected in this graph as are connected in this graph? Now looking at this one as we zoom in here, the first thing I might notice is remember there's two ways that we went about this. If you can just see the deformation, then that's a good way to do it. So for instance, what I might think of here is if I could imagine kind of pulling this vertice closer and at the same time this edge is shrinking, do you see it would look very much like this? So if you're comfortable seeing that and you're sure it's accurate, then that does make it isomorphic. But if we want to do more detailed comparison to be sure, then there are 4 vertices in each graph. Good. There is 1, 2, 3, 4, 5 edges in each graph. 1, 2, 3, 4, 5. That alone is not enough. We then have to compare, are the same degrees connected in both graphs? Do you all agree this is degree 3, degree 3, degree 2, degree 2? So it's like, okay, you've got 2 degree 3s connected to each other. Each of them are connected to degree 2. Well, we've got a degree 3 here, degree 3 here, each connected to degree 2. These are encoding the exact same information, so it is isomorphic. It's just the location of the vertice has moved slightly, and we've kind of shortened the edges. Now, if you haven't had a moment, consider our next one. Now looking here, before I get into the details, we always want to check the first things first, because if it's clearly not for a simple reason, it will speed up the process. So let's just count. The number of vertices for this one is 1, 2, 3, 4, 5. Whereas here, do y'all agree there's 1, 2, 3, 4 vertices? No more work needs to be done. If they don't match the basic information of same degrees or same vertices and same number of edges, then we don't even need to think about the more complicated step. So these are not isomorphic. Now, I'm going to give y'all a second to think about this. What if I changed it? So new problem. What if I put another vertex here? So before there was only a vertex here and here. Now I've had 1, 2, 3. Now think about the problem. Kind of imagine, what if I kind of pulled this one out, and as I did, this came towards the center, and this edge shrunk? Do y'all agree we would get the same graph? So this is pulling out to the edge, while this is going to go in the middle, and these edges are going to shrink to where it fits something like this, and then we just turn it 90 degrees. So if you like, you can see it that way. Otherwise, we can do our counting procedure. Now both of these have 5 vertices. They each have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 edges. Meets the basic criteria. Then we do a degree comparison. Degree 2, degree 3, degree 2, degree 3, degree 2. So let's see. Degree 2, degree 3, degree 2, degree 3, degree 2. So let's check. Is a degree 2 connected to both degree 3s? Yes, check. Are the degrees both then additionally connected to the other degree 2s? Check. So these would be with this additional vertex isomorphic, if that had been added in. Okay. Now let's review our definition of walk, path, and circuit. Remember, a walk is any direction of go from this vertex along this edge to this vertex along this edge, etc. And it's a walk if you don't leave the graph. So if it sends you from one vertex directly to another vertex that are not connected, that's kind of walking off the graph, so you're no longer a walk. So for instance, do we see I could not go directly from E to A because there's no edge listed, but I could go from E to C to A. Okay, so if it is going along allowable edges, that makes it a walk. What makes a walk into a path is a walk, so it's going along allowable edges, but it's not going to use an edge more than once. Now, if you have a path, to become the stronger definition of a circuit is a path, which means it's a walk that doesn't use an edge more than once. And on top of that, it begins and ends in the same place. So if y'all would think and label each of these as walk, path, or circuit, if multiple definitions apply, then write the multiple definitions. Now, a common hint for these problems is, like all the graphs, I encourage you to write them on your paper so that you're not just looking at the computer screen, you can interact with it. So say I've drawn this on my paper. Now let's trace out this and see if it goes along all the allowable edges. So from A goes to B. I could have taken either edge, but let's just say I took the straight one. B goes to D, good so far. D goes to C, good so far. C goes to E. Did I stay on the graph? Yeah, so it is a walk. Did I ever repeat an edge? Good, I didn't repeat, so it is also a path. Did I begin and end in the same place? No, so we've got to stop short. It's not a circuit, but I could rightly say that it's a walk and a path. Okay, now similarly, we're going to trace out our next one. So let's say we go from A, goes to B. Now I just choose to took the more loopy edge. You could have done this straight away at that point. It doesn't really make it clear which one. But I went from A to B, then from B to D, only way to go. Now, can D go directly to E? No. Do y'all see that would have me going here, but there's no edge. So what do we automatically know? It's not a walk because it's have us leaving the edge. And if it's not a walk, do you even entertain path or circuit? No, because those are building definitions. So we would say none. So we wouldn't select any of them. Or we could say not walk, not path, not circuit. Okay. Depending how the question was phrased, we know how we would answer it. Now checking our last one. So we're going to start at C, and it says, okay, from C go to D, from D go to B, from B go to A go to C. Did we only go along allowable edges? So it is a walk. Did we use an edge more than once? No, so it is a path. Do we begin and end in the same place? So in this case, it's walk path circuit. Good. Now, next up, we learned the idea of Euler circuits. So this is starting in 14.2 section of our notes. So which of the following graphs have an Euler circuit? Remember, we had a nice rule. A graph has an Euler circuit if every single vertex is even degree. So to answer this question, all you have to do is count the degrees of every vertex. If they're all even, the answer is yes. If even one vertex has odd degree, the answer is no. So for this, I'm just going to start labeling the degrees. Two edges coming out of this, so it's degree 2, 1, 2, 3, 4, degree 4, 1, 2, degree 2, 1, 2, 3. At this point, should I keep counting? No, since 1 is odd, we have no Euler circuit. I even have to continue. Okay, so next I count the degrees of the next one. Two vertices, 1, 2, 3, 4, 1, 2. Okay, so all of the vertices here are of even degree, so the conclusion is it will have an Euler circuit. Actually, many. So remember, the existence is just a degree counting argument. If they're all even, it does have one. If even one or more is odd, it does not. Next up, we could ask to find one. Now here, there's going to be many such examples. And if y'all remember from our previous exam, the way this was tested is you were kind of given a sequence and you had to select which vertice would make it an Euler circuit. So actually, let me do that here. I'm going to route it a sequence of vertices with one missing, and you have to decide one or more missing what you'd have to do to complete it and make it an Euler circuit. So if y'all would think about what goes in these blanks to make this an Euler circuit for the graph shown. What letters or vertices would you have to place here and here? So I think here it's helpful to kind of mentally trace out what's shown on the path. So if we go from A to G, G to B, now do we agree here I could either go to C or to F? There's only two choices from here. I don't know where I go next, but it tells me I end up next at C. And then, so I'm going to mark which edges we've used. So say I've drawn this on my paper. I'm kind of marking off as we go. Don't know what happens next, but then I end up at C. C goes to E. E goes to D. D goes to C. C goes to I don't know, but then I go back to here. So in order to make this an Euler circuit, all of the edges have to be used. And I can't repeat edges. So do we agree after I was at B, I would have had to go down to F, and then from F up to C, and it would use those two edges. And in order to complete my path from C, I had to cross along to B to be able to go back to A. So of course you could find your own Euler circuit, but just due to the nature of how the exams work, this helps it be computerized graded. So you'd be given a certain sequence and you select what are the vertices that make it an Euler circuit. Any questions there? Would y'all agree that drawing out the graph and kind of tracing over what you've already used is helpful? It helps you focus on what is remaining. Now, if possible, find the Hamilton circuit. So remember, Euler cares about edges, Hamilton cares about vertices. So an Euler circuit is a circuit that uses every edge exactly once and begins and ends in the same place. And Hamilton circuit visits every vertex exactly once and begins and ends in the same place. So it's not necessary that we have to visit every edge for a Hamilton. Now, Euler circuits have a nice rule to determine if a graph has them or not. If every edge is even, it has an Euler circuit. Hamilton circuit, there's no such nice statement. But since Hamilton circuits are a little easier to find, it's pretty much you just check if it has one or not. So for instance here, what if I want to visit every vertex? So could I just kind of go around the edges and then peel into CC to G back? Do we agree that would be a Hamilton? So if I could find one, it definitely has a Hamilton circuit. Now, you'll notice that doesn't visit every edge, but that doesn't matter because Hamilton circuits just care about visiting every vertex. Does it make sense why this one would have a Hamilton circuit? Are we comfortable with that? Now, one thing to look out for Hamilton circuits is this doesn't always occur, but if you ever see it, that's a dead giveaway it won't have a Hamilton circuit. If there's ever a squeeze point. Because imagine I started at E, then do we see if I started going along this way, to be a circuit, don't I eventually have to come back to E? Do y'all agree? So once I pass through, I've already used the vertex D once. Do we agree any path I draw would force me to go through D again, which would be the breaking of a Hamilton circuit? So if you ever have between, like you've got two sides of the graph and it all squeezes down to a single point, because you'd have to double cross that point, you know definitely there's not a Hamilton circuit. Okay, and this is the issue. Now, if y'all would, sometimes we like to change the problem just to make sure that we can understand it well. So what if I change the problem and I added this additional edge? Would there now be a Hamilton circuit? Yes, because while I might use D the first time, you'll see I no longer have to pass through D again the second time. So this would have a Hamilton circuit, whereas the original one would definitely not, because any path we took would involve visiting D at least one more time. Now I say describe the following, and what I mean by that is think about whether it has a Hamilton circuit or an Euler circuit. Remember, some graphs have neither, some graphs have one or the other, some graphs have both. So the first thing I would do is I would see, does each graph have an Euler circuit, by saying, is every vertice even degree? If so, you know it has an Euler. And then see if you could come up with a Hamilton circuit. So we've got two separate problems here. Now for this first one, I'm first going to check Euler circuit because that's the easiest one. See if every vertex is even degree. Degree 2, degree 2, degree 4, degree 2, degree 2, degree 4. Do y'all agree that since everything is even degree, it does have an Euler circuit? Now, I know I don't have a nice rule to figure out if it has a Hamilton circuit. I just have to kind of try to find one. So let's see if I can make a path visiting every vertex exactly once and coming back to the center. A to C, C to D, D to E, E to F. Okay, now that one was ill-fated. Let's see if I can maybe find a different one. A to E, E to B, B to C. Okay, now what do I notice is going to be the problem here? At this point, I can't, anywhere else I go, I'm going to have to pass through C again to get back to A. So maybe starting at A is the problem because it only has two locations, right? So let me see, maybe I could find one starting at E. You kind of have to try and error. Just because one doesn't work doesn't mean there's not one. You have to try a lot to see. Okay, so I'm going to go from E up to B. I'm going to one with more degrees. Here, here. And y'all see that would cause passing through E again. Okay. Let's try one more, but I think we're getting indications. So from C to D, D to E. Okay, if I go to F, I'll have to pass through C. Can't do that. If I gone from B, I'll have to pass through C again. You'll see, because there's no like outer loop among all of these, I can't just go along all the loops, and it's going to involve crossing back and forth. So this one has no Hamilton circuit. So it does have an Euler circuit, but it does not have a Hamilton circuit. Because anywhere I start, since there's no outer loop, I'm going to have to cross the same place at least once, right? Now looking at this next one, I see vertex A is degree 3. So would y'all agree we know Euler circuit is automatically out? However, Hamilton I think will be nice because we have this outer circuit that we were looking for. I could just go along the outside edges and I hit every vertex exactly once. Okay, so next up, let's identify if the following are trees. Remember, whenever you think of trees, think of the phrase minimally connected. That's the idea. If you got rid of a single more edge, it would be a disconnected graph. And particularly the thing that trees avoid are circuits, any kind of loop throughout vertices. So look at the graph, and if there's no circuit, i.e. kind of a loop, I could go here and eventually get back to where I started without reusing an edge, then it's a tree. Look at this graph. Does it kind of make sense? If I had enough space, couldn't I unfurl it and it would just turn into a straight line? It looks bent, but nothing is connected to make it into a cycle. You could just start unfurling it and it would become a straight line. In which case, it's definitely a tree because there's no cycles within it. It is minimally connected. If I got rid of a single edge, it would become disconnected, right? So this one is a tree. And if it helps, just imagine, what if I got rid of this edge? Do we agree the graph's now disconnected? For any edge I choose, if I got rid of it, it would make our graph disconnected. So this is a tree. But this next one, the key detail is this edge. This edge is what allows us to say, oh, look, we've got this cycle. Going along these edges, I could get back to where I started without repeating myself. And specifically, now do we see, because we've got this extra connection here, if I got rid of this edge, the graph is still connected. So I've got what we call a cycle. So this is not a tree. So trees are minimally connected. There should be no cycles. There's only one way to get from a vertex to another vertex. So just to illustrate that further, if y'all would, for both graphs, think about how many ways could we get from the first yellow dot to the second? In the first graph, does it make sense there is only one way? Right? Because there's no cycle, you've only got one choice. And that's the whole point of a tree. There's only one possible path between any 2 points. But for our next graph, couldn't I go out this way and I get there? But I also could have decided to just go this way. So if there's multiple paths between vertices, it's guaranteed to be not a tree because of the cycle nature. Now, if y'all would think about whether this graph is a tree. So in considering whether this is a tree or not, do we agree our focus would be here? Because this is a cycle, which makes it not a tree. Multiple ways to go about the path. So this would be not a tree. And our next topic that we're going to talk about is how do I take something that's not a tree and by deleting edges turn it into a tree, which is the idea of spanning tree. Now, the whole idea with spanning trees is remember you're only allowed to delete edges. You've got to keep the same number of vertices and you can never add edges. So it says find 3 spanning trees for the graph. Let me draw just a basic rubric of our vertices. We've got 1, 2, 3, 4, 5, 6, 7. And so that it's easier to work with, I encourage you to try to draw it somewhat related to their general layout so it's visually similar. Okay, so I've got these vertices. Now remember, when it's a spanning tree, our goal is to break the cycles. And the cycles are those kind of edges that interconnect and form a loop of sorts. So looking, would y'all agree this is a cycle of 3 edges, goes in a pattern? Okay, I've also got, this is a cycle. There's actually quite a few cycles here. This is a cycle, this is a cycle, this is a cycle. And then we've got even bigger cycles that we need to break. So let's just start choosing some vertices to draw, and then we just want to make sure that we don't overconnect it, and then we can still get from any vertex to some other one. So we can't be disconnected. So let's say I'm going to keep this edge. Can I add in this vertex? Good, I'm seeing no's, because do y'all agree that would actually add an edge that's not there? The only thing we're allowed to do is delete edges. So I could not add that last edge. However, this one was connected to this one originally, so I could do that. Now, this one was connected to this one. What do y'all think about connecting it again? Because I'm not adding an edge. So while I'm not adding an edge, do y'all see that based on the ones I already chose, that would create a cycle? So I don't want to have that one connected. But next up, this one was connected here, so let's do that. Maybe I like to keep this connection and then this connection. Could I add in any more connections that were in the original graph? I would say no, because any of the extra connections, for instance, these two were connected in the graph, that would make a cycle. Can't do that. These two were connected, but that would make a cycle. Can't do that. This was connected, that would make a cycle. Can't do that. These were connected, but I can't connect those. So I have deleted edges in a way that it makes my graph a tree, but I still have all the vertices eventually connected to each other if I go along different paths. And let's just focus on which edges did I delete in the original graph. I got rid of this one. This one. This one. This one. And that one. If you get rid of those edges, you get exactly the picture that I drew below, right? Okay. Now, if you choose to get rid of different edges, you're going to have a different tree. So if y'all would similarly draw 2 separate trees here based on deleting different edges. Now yours might differ from mine. Remember to check your work, just see, make sure I didn't add any edges that weren't there originally. I only deleted edges, and my result's still a tree that's connected. So for mine, I might keep this edge, this edge, this edge. Would that be a tree? Good. Now let's see, what else could we do? We could instead keep these ones, and that would also be a tree. Do y'all agree in all of these cases, if I added even just one more of the original edges, it would stop it from being a tree in each case? Because the tree is minimally connected. Taking away one more edge disconnects the graph. Adding one more edge in the wrong place would make it no longer a tree. If y'all would think here, we've got our original graph. Think of which of the two options to the right is isomorphic to the original graph. Now here I'd encourage us to pay attention to the details. Even though these vertices are close together, do we see they're not connected? So this is not a cycle. If I wanted to, I could imagine grabbing this vertex and just pulling it away, right? The key thing to focus on is the first thing we check is, before we get into the details, let's just make sure that they fit the basic requirements. Same number of vertices, same number of edges. So for the first one, we have 1, 2, 3, 4, 5, 6 vertices. Let's see if they meet that at least basic requirement on the other side. 1, 2, 3, 4, 5, 6, 7. Since the number of vertices is different, what do we immediately think? No to option 1. That's the minimum requirement. Now let's check option 2. That's not enough, but it's at least indication that we could continue with our thoughts. 1, 2, 3, 4, 5, 6. So they both have 6 vertices. Let's now start counting the degrees. Degree 1, 2, 2, 2, 2, 1. So in my mind, I'm going to ask, okay, is the other side have 4 degree 2s all connected, each bookended by a degree 1? So degree 1, degree 2, because there's 2 edges coming out, 2 edges coming out, 2 edges, 2 edges, 1 edge. Do we agree this is the same? And if you prefer the more like manipulation in your mind to see if they're the same instead of the counting, could we imagine straightening this one out and then maybe just flipping it over and you'd see the exact same? So if y'all would similarly attempt our next one, compare the original to option A and B. So let's do a vertice count consideration. 1, 2, 3, 4, 5 vertices in the original. 1, 2, 3, 4, 5 in A, so we can't disqualify it yet. 1, 2, 3, 4, 5. So both A and B have 5 vertices each. Now let's do a degree consideration. Degree 3, degree 3, 2, 3, 3. Okay. Now this vertice is degree 4. Do we agree since there's no degree 4 in the original, option A is definitely out? Now let's verify option B does work. This is degree 3 because there's 3 edges coming out. Degree 2, degree 3, also degree 3, also degree 3. So in the original, we had 4 degree 3s all connected to each other, which we do see is the case, with 2 of the degree 3s, the ones that did not have the diagonal, connected as well, which matches to the degree 2. So option B is the isomorphic graph. So here, let's identify which of the following are graphs. The first thing that I notice is, do we see this edge starts at this vertex, but then it doesn't end in another vertex? That's a dead giveaway that this is not a graph. Every edge must begin and end with some vertex. You can't just go to the middle of nowhere and stop. Now, our next picture, every vertex and every edge is connected to a vertex at the beginning and the end. So this one would be a graph. Next, let's look at these 3 graphs and identify which would be a simple graph. Remember, a simple graph is the stronger definition that not only is it a graph, but every pair of vertices is connected at most one time, so you can't be connected more than once to a single pair of vertices. And there can be no loops, whereas a loop is an edge that starts from one vertex and then ends at the same vertex. So take a moment to consider which one of these are simple, which ones are not simple, and I'd recommend you pause the video, think about it, and when you're ready, unpause to check the work. So here we see that this graph is not simple because this pair of vertices is connected by 2 edges. So any pair of vertices connected more than once is not simple. This graph is not simple because of this loop. That is a edge that goes from a vertex back to itself, so that's not simple. Now this graph, a lot of times students confuse the arcing edge with necessarily making it not simple. But remember, just because the edge is arced doesn't mean it's not simple. The key idea is this connected more than once? And do we see for these 2 vertices, they are only connected one time. All the other pairs of vertices are only connected at most one time. So this makes it a simple graph. Whereas in our other example, this was not simple, not because of the arcing edge, but because there were 2 edges between the same pair of vertices. This is what made this graph not simple. Now, as we're looking at this problem, if we would consider for this graph, what are the number of edges and what are the number of vertices? I'd encourage you to draw this picture clearly on your paper and then count once it's on your paper to make sure you're not double counting. I encourage you to pause the video, attempt this on your own, and then unpause to check your work. So here we know the number of vertices. We've got 1, 2, 3, 4, 5, 6, 7. 7 vertices. And then with the number of edges, I'm just going to highlight so that I know not to count it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. So next, let's look at the problem. The sum of the degrees of a certain graph is 34. How many edges are there? And as we're thinking about this problem, remember the nice rule that we had, that the sum of the degrees of vertices is twice the number of edges. Give everybody a moment to think about how we would solve this. Now we would set 34, the sum of the degrees of the vertices, equal to twice the number of edges. We solve and we get there must have been 17 edges in this graph.